This is Mrs. Palmer-Quay with the fourth video for Module 15. In this video I'm going to talk about acid-base ionization and pH. We talked a little bit about acids and bases earlier in the year. If you remember the definition that we used in the textbook, and this is the Bronsted-Lowry definition of an acid, is that a compound that will donate a hydrogen ion when it is in solution, and a base is a compound that will accept that hydrogen ion in solution. And I have a picture of here some common household acids and bases, and if you remember we did some testing of the pH of these various substances, and I'll talk a little bit more about pH later in this video. If we wanted to make hydrochloric acid, we would start with hydrogen chloride gas and dissolve it in some water to make a solution. And the solution would end up containing a hydronium ion, which is a water molecule with an extra hydrogen proton attached to it, and a chloride ion. And so in this case, this extra hydrogen on our water has been donated by the hydrogen chloride. And of course then the chloride ion is what is left over. So in order to donate that hydrogen ion, the hydrogen chloride first had to ionize. It had to separate into ions. And we also sometimes see the word dissociation used when we're talking about acids and bases. So this little picture down below is trying to give you an illustration of that. If we have our compound that's going to become an acid, when it goes into solution, it divides into the individual negative and positive parts. And even though we talk about it donating a hydrogen ion, or a hydrogen proton, because it's in solution, what happens is you end up with this hydronium ion being the thing that's carrying the hydrogen. But usually just for ease of talking about it, we don't talk about the hydronium ion in particular, and just when we say hydrogen, it's as if it's just the proton, but chemically, we're really talking about hydronium. So anyway, in the case of a strong acid, which is this beaker here on the left, you can see that you have a high degree of ionization or a high level of dissociation, that actually 100% of the acid molecules that fall into that water are dissociating, are ionizing into the separate negative and positive ions. Whereas on the right, this beaker contains a weak acid, and you can see from the picture there that a weak acid, when the acid molecules go into solution, a lot of them stay together. They don't ionize, so that it remains bound as a compound. It doesn't dissociate or ionize into two separate ions. So that gives you the definition of a strong acid versus a weak acid. A strong acid will ionize to a very high degree. Most of the ions will move apart from each other when that compound is put into water, whereas a weak acid will only ionize to a small degree. We can also say that our strong acid reactions go to completion, that they go past the point of equilibrium and go all the way to the products, where our weak acid solutions are in an equilibrium setup where the reaction favors the reactants more so than the products. So as I just hinted at, acid and base ionization reactions are reversible reactions. They can reach a point of equilibrium. And strong acids and bases favor the forward reaction. Very strong acids and bases pretty much go all the way to completion and at 100% ionization, so that their equilibrium constant would be very, very large, almost reaching infinity, because the reactants in the denominator would be such a tiny number. You'd end up with a huge number at the top. Then weak acids and bases would favor the reverse reaction, sort of the maintaining of the reactants without very many products, and the equilibrium constant for these reactions would be less than 1. If you remember, acid formulas, because they donate a hydrogen, generally start with hydrogen, or if they are an organic acid, they would end with this COOH as a typical formula for the organic acids. So we've got hydrochloric acid and sulfuric acid listed here, and then this is acetic acid written in a way that shows you that it is an organic acid. It's an acid made by a living thing. Your bases typically are either soluble metal hydroxide compounds, like that sodium hydroxide we've used a lot in lab, or maybe some potassium hydroxide. There are some hydroxide compounds that are not soluble, so they don't make a strong base. But you also see some covalent compounds that ionize by accepting the hydrogen ion, ammonia being one. Ammonium ion then forms from the ammonia. And nitrogen just seems to be something that does this very well. So another base compound that contains nitrogen is methylalamine, and I've written out the formula here. So it would accept a hydrogen to become NH3 with one positive charge. You can write specific acid and base ionization constants instead of saying an equilibrium constant, since we're talking about an acid reaction or a base reaction. Then we can have an acid ionization constant that's Ka instead of Keq. And again, Kb for a base ionization constant. But actually you calculate this just like you're doing the equilibrium constants, where you have a ratio between the product of the concentration of products to the product of the concentration of reactants. Just to give you an example for a general acid, this is just a general formula. Acid, just H again, hydrogen first. Some acid makes that hydronium ion, or as I said, we probably would just write H plus to make it a sort of shortcut. So the positive and ionizes into the positive and negative ions. These are our products over here on the right. So they would end up on the top of our ratio, our fraction that we're making to determine the ratio, and then the acid itself that you start out with your reactant on the bottom. You'd plug in the numbers that you'd be given and just solve. I'm not going to go through a math on one of these because they basically are so similar to the equilibrium constants. I figure you've got it. Water will ionize when water molecules collide. They can form this hydronium and then a hydroxide ion. So two water molecules, if they just hit with the right amount of energy and at the right orientation, the collision theory of reactions, remember, you'll end up with a hydronium ion and a hydroxide ion. And in pure water, the concentration of hydronium and hydroxide ions are equal. But in an acidic solution, you end up with more hydronium than hydroxide. And in a basic solution, there are more hydroxide than hydronium. So then when we're talking about how are we determining whether something is an acid or a base, on the chemical level, we're looking at what's happening between hydronium and hydroxide. So if you add a substance that will donate hydrogen, then you'll end up with more hydronium because those donated hydrogen will be picked up by your water molecules and make hydronium. And conversely, if you add a substance that will grab the hydrogen away from the water molecules, then it'll turn those water molecules into hydroxide ions instead of leaving them or taking them away from the original amount that were there in the pure water solution. So that is how the self-ionization of water then is connected to the acid-base determination for any particular solution. We use this ionization of water as the basis for the pH scale. pH stands for the power of the hydrogen ion, or sometimes you see it as the potential hydrogen, and is calculated as the negative logarithm of the hydrogen ion, or more particularly the hydronium ion concentration. So the concentration of a hydrogen ion in pure water is 1 times 10 to the negative 7. That would be for your hydrogen ion, or as I said, more accurately, it's your hydronium ion. Since it is equal to your hydroxide ion, in case you were curious, your hydroxide ion would also be 1 times 10 to the negative 7. Now we use this number for the hydronium ion, and if we put it into this formula, the negative logarithm of that number, then you get the answer of 7 representing the pH of pure water. And that is taken as the midpoint or the neutral solution. So that anything that has a pH of less than 7, which would be something that would have more hydronium ions, since we're dealing with exponents that are negative numbers, if something had 1.0 times 10 to the negative 3, even though this is a smaller integer, since it's a negative, it's actually a bigger amount. And so this would have a pH of 3, and that would be a sign that it was an acid. Whereas pHs that come up larger than 7, so that your exponent would be to a negative larger number, like say 1.0 times 10 to the negative 10, then the pH, this would be an even smaller amount of hydronium or ions, or the hydrogen ion. And so even though your exponent is a bigger number, since it's negative, it's representing a smaller actual number, and these are your bases. So the pH scale really indicates how many hydronium ions are present. The book is kind of deceptive in the way it's talking about the pH numbers. They're saying that pHs below 2 are strong acids and above 12 are strong bases. But really, a strong acid is an acid that dissociates completely. And if you have a very low concentration of a strong acid, you can come close to a neutral pH because there's so little acid in there, you don't notice it. And conversely, you can have a very high concentration of a weak acid, an acid that does not ionize or dissociate very much. But you've got so much in there that you've just loaded it up with hydronium ions, and so the pH is going to register a dangerously low amount. So the only time that the definition from the book that says pHs of below 2 are strong acids and pHs above 12 are strong bases, the only time you can really say that is if you're comparing different acids and bases at the same concentration. If you line them all up with the same molarity, yes, you can make those kinds of distinguishing criteria. But if you're just talking about the pH, we can't tell from just the pH whether the acid or base that made that pH was strong or weak, because it depends so much on the concentration. That's what really matters. I also wanted to point out that each whole number increase in the pH is actually an increase of 10 times. So if we start with our pH of 7 in the neutral setting, when we go to a pH of 6, we're actually 10 times more hydronium ions present. So it's an exponential, a logarithmic scale. Every time you change one integer in the scale, you're actually having a 10-fold increase or decrease in the number of hydronium ions, so that the number differences actually are bigger than you might think. If, oh, I'm just going from 6 to 7 or from 2 to 3. No, it is a much, much bigger difference because it's 10 times that. You can look over here on the right and see some of the examples of some common pHs. And really pHs, if you see here at pH of 2 and 3, we've got things like lemon juice and vinegar. Well, you probably don't want to drink straight lemon juice or vinegar, but we certainly drink grapefruit and orange juice and some of our carbonated beverages, which will have a pH of 3. So even though it is seems to be a small number, because of that 10-fold increase every time you move up another integer, there's a really big difference between a pH of 2 and a pH of 3. On the other end, some of our more basic solutions, we've used ammonia in the lab. Even soapy water might be slightly basic. And of course, the ones you need to worry about are things like bleach and oven cleaner and drain cleaner, which is basically sodium hydroxide or lye. So this just gives you examples of some of the things that are part of the found within the pH scale, some of the compounds that are acids and bases. So this finishes up what I wanted to cover with pH, and this is the last video for Module 15.